All right, guys. So today we take a short pause to review certain key ideas that we might need. And I like to begin the review of infinite series and sequences in the following way. So I am rather generous with money. And so if you'd like me to do so, I will give you right away 2 to the power of 7 plus 2 to the power of 8 plus 2 to the power of 9 plus 2 to the power of 10 and ad infinitum dollars. Yes? Now my question is, of course, all you have to do is ask and sign. Like you need to sign right in my chat that you want this money to be handed to you. And I will do so. Go ahead, guys, think about it for a moment and let me know if you want this deal. Okay, Sarah wants it. Fnu wants it. That's good. What about the rest of you? Come on, guys. Do you see a good deal or you see a not good deal? A bad deal. Okay, here we have Frederic wants this. I will take only your time. Jack. Well, you all take my time, sure. You bleed me over it. But do you want it or not? Of course, if you want it, you like the word it, of course. What does the word it refer to? Okay, a lot of people signed. What does the word it refer to? Well, it refers to money, I presume, right? So how much money will you be getting? Okay, the infinite amount of money. Let's try to see what happens. Okay, guys? So just as Alan mentioned, it should remind you of a Mandelbrot set, and that this sum has itself within itself, right? It contains itself as a sum in some sense. So in this particular way, you can try to figure it out. So the sum equals to 2 to the power of 7 plus 2 to the power of 8 plus 2 to the power of 9 plus 2 to the power of 10. And I put everything after 2 to the power of 7 in red parentheses. Do you understand why I did this? Because what's in the red parentheses looks very much like the original sum. Good? And all I have to do is factor from the red parentheses a 2. So now I have 2 to the 7 plus 2 times 2 to the 7, 2 to the 8, 2 to the 9, which is exactly S. You follow what I just did, guys? And so we reduce this complex equation to something rather very simple, right? S equals to 2 to the power of 7 plus 2S, where S is the sum of money that you will be getting. Upon solving this equation, you see that S is equal to minus 2 to the power of 7, so minus $128. So Sarah, Fnu, and I guess Fiona and everybody else that decided to participate owes me $128. Good? Do you have any objections? Anybody wants to voice some objections to how this was calculated or this process? Or, of course, I'm the instructor, so you don't dare to voice any objections. Okay. Jack, you have any objections to this?
So my question is, if you, let's say if you take out 2 to the second power from the S lookalike, right?
If I factor out 2 to the power of 2, yes?
Yes, from the S lookalike S.
Okay.
The amount changes, no?
Well, let's try to see. Let's see if the amount changes or does it stay the same, right? So we can try to see what happens if we can consider a generic series. Why not, right? Let's consider S equal to ARM plus ARM plus 1 plus ARM plus N and onwards. Yes, and onwards. So there are many things you can do, right? So one aspect is maybe you can start adding it up. Let's say, in other words, you notice that similarity begins after M plus N, right? So different similarity, you can put parentheses there, right? In other words, maybe that should be a question. Does the sum change if I calculate it a different way? So I can start doing it from here. And that would be then, it would be ARM factored out. If you kind of solve it, it will be ARM factored out R to the power of N plus 1 minus 1 divided by R minus 1 and R to the N plus 1 minus 1. If R is negative, this would be, if R is bigger than 1, sorry, that would be with a negative sign. That would be with a negative sign. And the result, if you do it this way, would be ARM divided by R minus 1. So if you do it different ways, you have to, of course, you just investigate what situation can happen. Will the sum be any different? At least if you begin doing it this way, the sum is not different. It will be the same if you factor, if you consider, for example, the first n terms, or begin to factor for after the second term, it will be the same. Investigate it. If you want to think about it longer or discuss it longer, guys, we do that after class. Okay, we can investigate other objections to the summation. But you see, you have to be, of course, very careful. You're dealing here with infinity, and actually, that's what I'm gonna mention in a moment. Okay, so. What I wrote over here should be, if I'm not mistaken, Jack, we can investigate. It should be the same as factoring different terms. Okay, factoring different terms, it would amount to adding up more parts. Okay, and vice versa. So that should be equivalent. But if you want to, we can investigate if that is not. So in your email, at least, I did not understand why you say we will get different sums based on that. Naturally, if I start the summation with a different m, in other words, if I eliminate this first term and start with m plus 1, the summation will be different. And that is true.
Yeah,
okay?
That was my point. Yeah.
If you cross out ARM and you start with fewer terms, it seems, if it begins with ARM plus 1, then the summation will be different. Right, but maybe that's not a problem, right? You're expecting, certainly, perhaps that's the objection. So Sarah said, for instance, she expects infinite amount of money. Yes, so that's another objection you can say, is that the other solution to this equation is infinity, right? So infinity seems to equal to 2 to the 7 plus 2 times infinity. And why did I choose S to be a finite solution and not maybe infinite solution? Okay, that has to be, you have to be very careful, because at least in calculus, this symbol does not represent infinity. It rather represents a process called growth without bound. And we will talk about that a little bit longer and later when we talk about series. Okay, so when you sum such series in calculus, in Calc 2, you notice that the series is divergent and you give this symbol. But what that symbol means is that if I were to give you first 2 to the 7, and then 2 to the 8, and then 2 to the 9, as I keep giving you that money, the amount you have grows, the limit grows. Okay, but what is it that if I were to give you all the piles of money at the same time, that's a bit more complicated. Another objection is, of course, what do I mean by an infinite sum? If I mean sequence of partial sums, as I will review in a moment, then it's understandable, right? But if I mean, if I am saying sum everything together ad infinitum, it can be very vague, and vagueness is dangerous, okay? So, by the way, guys, it gives me the pleasure to introduce to you a wonderful word in German. So the word German gift, in German, it means poison. You should know that, right? So when a German wants to give you a gift, don't take it. All right, guys. So for probability theory, we have to investigate a few things. We will need sequences. So let's begin with a quick review of what sequences are and how to study them. So a sequence is just an ordering of items in the set X. That can be any ordering, right? That just what means somebody is first, somebody is second, somebody third. And mathematically, we define a sequence to be a function from the natural numbers to that set, okay? And instead of writing fn equals x, we simply write xn to indicate that, that this element was paired with the integer n, okay? And here is a natural example of a sequence. Fn equal to 1 over 2 to the n plus 1. And that just means if n is equal to 1, that's 1 over 3. If n is 2, it's 1/5, 1/7, and so forth. Good? And here we have another sequence, which is 1, 2, 6, 24, 120. You recognize it as the N Factorial sequence. So here I take an integer, and the formula is to multiply by all consecutive integers until I reach it. Good? So next we have to understand what it means for a sequence to converge. And that will be important for probability. So let's consider a very, very simple sequence. Consider the sequence an equal to 10 to the minus n, okay? So imagine that when you investigate the sequence, you can see only the first 5 digits of that expansion for the sequence. Make sense? So that means your epsilon, your resolution is 10 to the minus 6. How would you conclude that the sequence is convergent? Is that if you were to write the members of the sequence, you write the first term in the sequence. It's you can see 0.1 and a bunch of zeros. So you can distinguish this term from 0. For 2, you can still distinguish this term from 0. For 3 and for 4 and for 5, you can still distinguish from 0, but come 6, look at it. Because you can only see the first 5 digits, you can see 6 already looks like 0 for you. And 7 will look like 0 for you, and 8 will look like 0 to you. So if you look at this column starting from 6th position and onwards, the sequence looks to you like 0. If you have a better eyesight and you can see 8 digits, then starting from the 9th term, it all looks to you like 0. If you have even better eyesight and you can see 1,000,000 digits, starting from the 1,000,000th and first entry, it will look like 0. Do you understand? So convergence means intuitively is that if you observe that sequence, no matter who is observing, that person will conclude that the sequence converges to 0, okay, or converges to the particular number. The distinction seems to become so small that you no longer can detect it. Good? So any questions so far, guys? Good. Next, this inspires the delta epsilon definition. So we say that the sequence converges to L, the sequence AN converges to L, if for every epsilon bigger than 0, there exists a function n of epsilon such that AN minus L will be less than epsilon whenever the integer n is bigger than n of epsilon. You understand what is that n of epsilon? That's the first row from which if that's my resolution epsilon, n of epsilon is the first row where I stop being able to distinguish the terms of the sequence from the number L. Is that clear, guys? You understand what is capital N of epsilon? Very simple idea. It means that from that moment onwards, you cannot distinguish. So from that row and every subsequent row looks to you like L if your resolution is epsilon. Clear?
Professor, can you again tell me what's epsilon again?
Epsilon is your resolution, is how many digits can you see. So in this previous example, I made it very simple. Your epsilon was 10 to the minus 6. So that means you could see 6 digits. Okay?
Thank
you. Good? Up to, so yes, good, you understand? So after a while, you stop seeing. So that epsilon represents how many digits you will see. So epsilon is usually small, but it doesn't have to be. You understand? I mean, if your goal is to conclude that the limit is L for the sequence, then you want to take a person, or you take a detector that has a very good resolution, right? So the smaller the epsilon, the better is the resolution of the detector. But the principle is that every detector will be fooled into concluding that the sequence is identical with L starting from some entry, from some number n. You see? So if you look down the row, if you look down the column until you reach some n epsilon row, from that row, that detector is no longer able to distinguish the input from L. Clear? That's exactly what it means. Okay, I'm just talking. So you're talking about detectors. You're just trying to decide whether the terms of the sequence are exactly L or not exactly L. And convergence means that starting from some particular entry, some particular row, you no longer can detect that the input is different from L. And of course, you being a particular detector, so you have a particular resolution epsilon. Some other detector has a different resolution epsilon, but any detector eventually fails. They just don't fail at the same row necessarily. You understand? So one detector will fail starting from 6th row, and a better detector will start failing from the millionth row. An even better one will stop failing from the billionth row. But all of them eventually fail. You understand? Confirm, guys. Say yes, you understand. It's a review, but I'm not sure if you know it from before. Okay, good. Wonderful. Good. Good. So now let's consider some very important limits, guys. So for this class, let's see if you remember, what is the limit as h goes to 0 of 1 plus h to the power of 1 over h? Write in the comments if you remember what that limit equals to. Well, the limit, maybe it relates to a derivative, but what specific limit is this? What does it equal to, guys? Okay, 1, 1, 1, 1, 1. Yes, everybody can write. I want to see a lot of you telling me what this limit equals to. Don't hide from me. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, Alan, listening. 7 people. Continue writing. So what? So I see 7 of you are saying it's 1. Yes. 1 says something else. Okay. Okay. 1, 1. Okay. All right, guys. So my review is definitely not in vain, because anyone who wrote 1 are terribly wrong. So Alan and let's see who else. Let me remember. And Andre, thank you so much. Right. I appreciate your input, because you are right. The answer is also not infinity. The answer is only 2 people answered it correctly. Yes, Andre. Good. Andre and Alan. Thank you. Now let's see what the answer is and why, guys. This limit has a lot to do with solving the differential equation d dx fx equal to f of x. And recall that if you start with an exponential ax, okay, if you start with an exponential, the derivative of an exponential by the definition of the derivative, its limit as h goes to 0, f of x plus h minus f of x over h. I hope you remember the definition of derivative, yes, guys? And that's a to the x plus h minus a to the x divided by h. From here, I can factor out a to the x. And I observe that this limit is just the derivative of the function at 0. So I notice that derivative of exponential functions, guys, whatever that number is, the derivative of exponential functions are always constant times the original function, okay? Do you understand what this little segue derivation means? I am not solving it. Finding the derivative of an exponential is a pretty difficult task. But by playing with exponent rules, I noticed like this. Look what I noticed, guys. And if you want to, you can review my notes on Calc 1. I'm also teaching that. So what I'm just saying is you started at trying to find the slope at the curve at some particular point x, and you end up needing to find that slope at the point 0. Notice it was an arbitrary x, and you ended up finding it an arbitrary 0. Okay, so that means that the derivative of f of x is equal to f of x times f prime of 0. Of course, assuming that the derivative at this limit at 0 exists. You understand? Which means that if you take derivative of exponentials, the derivative is not very different from the exponential. Do you understand that? And so, guys, we make this inspired assumption that there will be, if you play around, you can play around with the calculator, but we have this inspired assumption that there exists some particular base. So maybe it's not 2 and it's not 3, but there exists a particular base, call it E, such that limit as h goes to 0 of e to the h minus 1 over h equals to 1. In other words, a curve where the derivative of the curve at 0 is actually 1. Why do we want such a number? Because then the c is equal to 1, and then we get a function whose derivative is identical with the original function. Good? Now, what we have about this number, we'll talk about it later, and I can tell you more about it if you want to understand how to figure such number, how to identify it. But we have that the derivative of e to the x is equal to e to the x, okay? And so we can now do the following, guys. Look at it. Limit as h goes to 0 of f of x plus h minus f of x over h. The derivative of this function, that function is e to the x here, right, is again equal to f of x, which means that if I don't take the limit, this quotient is very closely approximating f of x. It's not equal to it, but very closely approximating it. Are you with me? So guys, don't just stare into my headlights, right, to my soul-killing eyes, but just tell me if you understand or not. Okay, if you are stuck on something, then make sure that I'm not just wasting my time. So what happens here, guys? I can drop the limit, and I have this approximation. So look what it means. For very small h, I can rearrange this equation. Just multiply by h and add f of x, and then factor it out. Look what happens here, guys. F of x plus h is very similar to 1 plus h times f of x. I wrote this iteration. You see what I did? I'm playing with my derivative formulas. Now, this looks like a recursion, because what does it mean? I can say this is a number. It means that a function that a number is essentially equal. This is very close to equal. 1 plus a small step, the function evaluated at the number minus the small step. Do you understand? I just look at the letters and I see, okay, I can figure out what the function is at some number. I just take 1 plus a small step, multiplied by the function evaluated at the number minus the small step. Now, I want to walk back to 0 because e to the 0 is 1. You understand? I'm gonna do recursive iterations until I go all the way back from my starting point x to 0. Okay, this is basically how what I observe. I observe that I can rewrite. Notice I'm not using the same symbols. This just means f at a number is approximately 1 plus the small step times the function at the number minus the small step. It's not easy, guys, right? So people that take my calculus, they go through it. I'm not sure if they remember, but I make them go through that reasoning. Do you understand that reasoning? You understand? All I'm doing is I'm taking a sentence and I'm just rewriting it in a more convenient way. I am just deriving an iteration. I have this formula. Do you understand how I obtain this formula? It's not exact reasoning. It's not precise because limit is something I dropped and therefore I made an approximation here. I'm saying that f of x is approximately 1 plus h times f of x minus h. So then we are going to take the interval from 0 to x, and we are going to divide that interval into n steps, where n is huge. N is billions and millions. The bigger, the better. You understand? N is a huge number. And I made, of course, exaggerated size steps so that you can actually see them. Yeah, so that you can actually see them. Guys, after class, if you have time, stay with me. I will re-explain it if you don't understand something. Good? So if you're ashamed to ask me in the middle, then wait after class and we can talk about it more. You see this? This is taking one step back. So h is equal to x divided by n, this interval divided by n. That's one step back, then another step back, then another step back, and I will do that until I reach 0. Here is my first step. The function at x is similar to 1 plus x over n, that's my step back, f of x minus x over n, which now I will take from here, I will take another step back. So because this part is very similar to 1 plus x to the n, x divided by n, sorry, times f of x minus 2x over n. You understand? So because we had this extra 1 plus x divided by n, I have it squared. Good? You look very sad. Which makes me feel it's not good. And so I continue taking those steps until I have subtracted n steps. And what do I get? I get that the result is 1 plus x divided by n to the power of n, f of 0. And f of 0 is e to the 0, which equals to 1. Do you understand? So I have here 1 plus x over n to the power of n. So where n is huge. In particular, I observe that e to the x equals to limit as n goes to infinity of 1 plus x over n to the power of n. The answer is e to the x. Now let's carry out a calculation, guys. Now that you understand it, a is equal to what? B is equal to what? C is equal to what? D is equal to what? Okay? Calculate it and tell me. Okay, so A is e to the 1 and B, Andre, thank you so much. Come on, guys, answer. Yes, exactly, Grant. Okay, so then B is, you see, what is x in B? X in B is minus 5, good. So we solved A and B, good. It's 1 minus, it's 1 plus minus 5 over n. So x is minus 5 here. Now, can you tell me what is c? Do you see what is c?
Wait, I'm sorry. Could you clarify? Is b e to the fifth, e to the negative fifth, or is it just negative 5?
No, of course it's not just negative 5. It's e to the minus 5.
Okay, thank you.
Do you understand this derivation, guys? E to the minus 5. It's a very simple derivation. You just have to understand one idea. First of all, do you understand that what we know about e to the x, we know two things about it, right? That's the assumption of this notes. We know that the derivative of e to the x is equal to e to the x. It doesn't change. And we know that e to the 0 is 1. Okay? And then from there, I can come up with a limit that estimates what is e to the x. Because what I do is I just take, this is the definition of the derivative at x. In other words, f prime of x means this limit. Now, if I don't want to take the limit, I can make h very, very small. And then this ratio is very close to the derivative, which is then for very close to f of x, right? And then I can rearrange and I can create a recursion. It says f of x plus h is approximately 1 plus h f of x, where h is very, very small number, okay? And that gives me an idea of how to write a recursive formula. It means that I just say the function at a number is equal to 1 plus h, the number minus h inside of f, okay? That's from this formula. Just here is a number, here is the number minus h. And then when I follow this recursion many times until I have eliminated x to 0, I walk all the way back. Over 0x, I walk all the way back to 0. So I partition this distance into n steps, where each step is going to be my h. If the step is very small, then that recursion is valid. Good? So I make all the steps back until I reach to 0. And I get 1 plus x over n to the power of n. So that's an approximation. And this approximation gets better and better with increased values of n. So in the limit, we know that in the limit f of x will be equal to 1 plus x over n to the power of n. Okay? If you are interested in more in this background after class, I'm happy to provide it. So Abhishek, well, a to the x, yeah, you have to be, of course, very careful. Depends where you begin from. So we're not solving for the derivative of a to the x. That will be the way I present it. Will be a bit deeper in calculus. Or if you want a very good presentation of it, you just ask yourself what is a function whose derivative is itself. And if you have a sense of what that function might be, you can construct a notion of exponential. Okay. So then we calculate all of those things, guys. And now what is c? C will end up also being e to the x. C and a are the same. Okay. D will end up being what? E to the 5. Yes, Alan, exactly. Okay, so and onwards, right? So here is the construction, guys. Here x is 1, here x is minus 5, right? And in general, we notice that the pattern that 1 plus something small to the power of 1 over something small will be e, okay? If that something is very close to 0, okay? And for the remaining values, you might have all sorts of worries. You might think, well, n is not general enough, so we can, if we understand what's the logarithm, we can take the derivative of a logarithm. We get 1 over x. And so the derivative of the logarithm at 1 is 1. And that means that if I take the definition of the derivative of a logarithm, you see, if I know already that the derivative of the logarithm at 1 is equal to 1, by definition, the derivative of the logarithm is this limit, okay? Which can be written, because ln of 1 is 0, can be written as 1 over h, ln of 1 plus h, good? Which I can push the 1 over h as the power, and I have ln of 1 plus h to the power of 1 over h. It's equal to 1, which means that e to the power of 1 will be e to the limit of this value. I forgot to write logarithm here, right? There is a logarithm here, which equals to e limit as h goes to 0, e ln of 1 plus h to the 1 over h. And so this is just limit as h goes to 0 of 1 over h to the power of 1 over h. That is my e, okay, e to the 1. And so in here, I can see 1 plus 5h. And so over here, I'm missing a 5. So I put a 5 and multiply by 5. That makes it e to the 5. You see what I do? Because as soon as I see the same input in the box and the input goes to 0, I know that what's in red now is e. But that is to the power of 5, because I never had a 5 here. Similarly, what happens here? It's 1 plus minus 2h. But here it's 1 over h, so I want a minus 2 in the box. So I put a minus 2, and I factor it out, and I have e to the minus 2. Do you see? Because that part is e, and that part is to the power of minus 2. And in general, for f, 1 plus x times h to the power of 1 over h ends up being this limit, which is equal to e to the power of x. Good? All right, so let's review series. So here is how you treat series in calculus. So we have that the summation a1, a2, a3 all the way, the summation of the sequence is denoted by the sigma notation, sum from 1 to infinity of a sub k. And the meaning of that in calculus is it's a sequence of partial sums. In other words, we have S1 is A1, S2 is A1 plus A2, S3 is the sum of the first 3 terms, Sn is the sum of the first n terms. You understand? So to avoid the problem of having infinity jack, we sum to a finite extent, and then we take the limit, right? And in that sense, that previous example that I gave you, in that sense, in calculus, you would have said that you get infinity, right? But you have to be, of course, careful. Is that what you really get? That's what you're getting as I am increasing the payments. If I'm giving you more and more payments, 2 to the 7, 2 to the 8, 2 to the 9, and onwards, your money grows. The amount in your bank grows. But what happens if I were to give you all the amount of money? You have to understand what that means. It may be even a vague question. But in some sense, you might be familiar with sums of the form 1 plus 2 plus 3 plus 4 plus 5 and whatnot. And there is a meaningful result which says that it's equal to minus 1 over 12. And you can search for it. You understand? So there are other notions of summations that are very important. Okay, good, guys. So we will say that this series converges if the limit of the partial sums approaches some value s. You understand? So again, a series is just a particular kind of sequence. And that particular kind of sequence converges just as any other sequence converges, right? It means that eventually you cannot distinguish the number you obtain in the rows, first row, second row, third row, nth row. Eventually, starting from some row onwards, it looks like the same number to anyone observing, to any fixed observer. You understand? The only difference between observers is that one observer will say, oh, it all looks like S, starting from the 6th entry, perhaps, and some other observer will not say that until the millionth row. You see, but all of them eventually agree that what they're observing is S. Good? So then, of course, you have the following simple consequences, guys. This is known as the divergence theorem. If the summation of the series exists, in other words, if the series converges, the limit of the term of the summed series, so the term sequence, must go to 0. An has to go to 0. Why is that happening? Well, let's look at it, guys. What is an? How do I obtain an? I take the nth sum And from that, I subtract the n minus 1 sum. Do you agree? The difference between them is a sub n. Do you agree? Now, what is the limit? Okay, guys, the limit of this sequence term is the difference of the limit of Sn and Sn minus 1. If they are convergent, Sn will start looking like S, and Sn minus 1 obviously will also look like S. Do you understand? The only difference between them is that Sn minus 1 is logging by one row, right? So what is Sn? It's here. Sn minus 1 is here, and Sn is here. You agree? If you are pushing n to be a large index row, then it drags the n minus 1 to also be large, right? So clearly drag it far enough and it will enter the blind region where everything looks like S. Every row looks like S. Clear? So the answer is that an is going to approach 0. So only summations made out of sequences that converge to 0 have a chance to produce convergence series, which is maybe obvious to you, right? Because I mean, the difference between the terms of the sequence must become negligibly small. Good. So here again is that example, 2 to the 7, 2 to the 8, 2 to the 9, and onwards. You can see that clearly the terms of this sequence that are the difference. This is A1, A2, A3, it's this 2 to the 9. A4 is 2 to the 10. Clearly, those do not converge to 0. So in the limit, the series will not be convergent. So the partial sums diverge to infinity, which is also obvious, okay? The summation, as you increase the sum, diverges to infinity. But be careful, guys, that is just a limit statement. The limit statement is not perhaps the same thing as the summation if you can define the summation in some meaningful way. Okay, that's not the calculus is not the only meaningful definition of the sum. You can come up with others that are in different contexts more important. Good. So guys, now we are talking about the simplest type of series. The simplest series is perhaps of the form ARM. Okay, Melissa has a question, and you're saying it. What is it? It is, you're talking about E, so you probably mean something here. Right?
No, I'm talking about like the 2 to the 7 plus 2 to the 8 plus 2 to the 9, like that.
Okay, and what about it?
How come in this example it goes to infinity, and in the very first example it went to
It's
E?
minus 128, the very first example. Right? Yes, exactly. Earlier, because I didn't say it goes. You see, I asked you what you want, and the question is, how am I going to give you money, right? Nobody is arguing here that if I begin giving you money, right, I'm giving you first batch of money, which is 2 to the 7, 2 to the 8, 2 to the 9. As I'm throwing the piles of money one by one at you, the number grows, right? The amount of money you have just grows and grows and grows, right? The question is, you see, I do it sequentially, right? When I do partial sums, I mean, I take the first pile, here you have it. Next, the next pile, next, the next pile, right? I'm adding that sequentially. But what happens perhaps if I shove all the money at you at once? So imagine, you can imagine the myriads of mountains of money. Kind of, you're seeing here is a pile of 2 to the 7 dollars. Here's a pile of 2 to the 8 dollars. You see those piles, and I push them to you on a tray at the same time. All of it at the same time, if that even makes sense, of course, right? The summation that you will obtain does not have to be the same. The process that by which you can sum it might be different process, okay? Which of course you have to be precise, you have to define it, okay? So the calculation I carried out at the beginning of this as a flavoring, it's a dangerous calculation. You cannot be convinced based on that calculation that what you have done is meaningful necessarily, right? It's a sort of, it looks like it's a good idea, but in that calculation, we assume that the answer is not infinite. We assume the answer is finite. If the answer is finite, then you're owing me $128. But if the answer is infinite, perhaps that's not true. The question is the answer finite or infinite, and in which context? So as I mentioned, guys, that if you study physics, or at least certain basic ideas in physics, usually when you get an answer that is infinity, that's a meaningless answer. Okay, that's the nature will do anything. Nature seems to prefer finite answers. Okay, so that means that somehow something must happen if physically, either to prevent me from being able to do that, or if I'm able to do something like this process, to give you a finite amount. Okay. Now the process that I described at the beginning is vague. So I mean, the question is what is happening there? It's very vague. Good. So don't take that example extremely seriously, but understand that by doing it, you're not being dogmatic. By seeing that that's a possibility, you think, okay, is there anything reasonable about minus 128, or is it complete nonsense? And you can see in some branches of mathematics, not through such justification, but through something much more intricate, you can show that the series, let's say 2 plus 2 squared plus 2 cubed, but not converges to minus 1. I can even show you a video about it. You see? The question is, what do you mean by summing? And so I'm saying that for the purposes of this class, and for most standard purposes, what you mean by summing is that you do it gradually, like this, okay? And if you do it gradually, the limit will be this sideways 8 symbol, which is, by the way, you call it infinity, but it's a wrong term. That sideways 8 symbol just means that the quantity grows and grows and grows as I keep giving you the piles, but it does not tell you what happens at the end of the process. And I can give you paradoxes if you're interested that I played with my calculus students, where it's actually from your probability book, one of them, right? Where the limit is very different from the actual outcome. I can show you a situation where you do a process similar to this one, where in one situation you get infinity and in another situation you get 0. Okay?
Okay, thank you.
Sure. Okay, guys, so this limit then by Calc 2 definition of what you do here, the Calc 2 process is producing divergence, and it will diverge to infinity. In other words, the numbers just explode. Now, geometric series. Now, the simplest series you can think of is of this form. So you have a constant times some number that you take to the nth power, plus the constant times the number to the n plus 1 power, then the number to the n plus 2 power, and so on ad infinitum. And this is known as geometric series, and it converges if and only if the number r that you raise to successive powers is between -1 and 1. Okay? And then let's see what it converges to. Now I'm going to use that same process I illustrated at the very beginning, because it's a very quick and nice process that gives you the right answer in all cases where you expect the answer to be meaningful. Good? Same process, look at it. I begin with the full sum, and I'm going to put in parentheses everything starting from the n plus 1 term and onwards, because what's inside of the parentheses looks like the original sum. All I have to do is factor out an r. Yes, factor out an r. And what do I get? I get that this result, it results in ARM plus RS. Okay, because that's just S. And then when I solve it, I have S minus RS, which is 1 minus R times S. It's equal to AR to the M. And so S is equal to ARM divided by 1 minus R. That's the sum of my sequence. Okay, now notice that in this case, this process always yields the right answer, because you understand when you have this is the problem, guys. You get back to this equation. This is the equation. S is equal to this thing. The solution is either finite or infinite. Here, if you take the limit process will produce, you can do it slower, in a slower way. We can take a limit process. I can show you how to do that if you want to just calculate the partial sum. that partial sum will produce a convergent sequence. Okay, so that we're seeing that the limit is tending to the finite solution. You see this equation? This is the thing. This equation, guys. The equation. Let me just type it out for you again. The equation S equal to ARM plus RS. The equation in the unknown S has actually two solutions. You know arithmetic, right? Either the solution is finite or the solution is infinite. Okay. Now, if you take that's the same thing that happened in the previous situation. In the previous situation, we just decided arbitrarily that the solution is finite, right? Whereas in this situation, if you take the partial sum approach, you will see that that the limit indicates that the solution should be finite. Whereas in the previous example, the limit is favoring the infinite solution. You understand? In the 2 plus in the 2 to the 7 plus 2 to the 8 and onwards, it seems that this limit of partial sums will favor the infinite solution. Whereas in this example, it would favor the finite solution. Understand? So yes, so in this situation, I have much better reasoning to dismiss infinity. In the previous situation, it's more of a sort of philosophy that infinity cannot be meaningful. But why can it be meaningful? That's a complicated question. Good. Besides, again, the true objection to this process is that this process is, even this one, is not rigorous. In other words, how do I know exactly, very logically, what am I doing? What is an infinite sum? Do I comprehend infinite sums? If I do limit of partial sums, that's in terms of concepts that I developed well. But if I see a summation that is not ending, what do I mean by it truly? It's a bit confusing, but sometimes hazy things are very important to be able to process. You understand? Think intuitively, and it gives you interesting insights, which of course might be wrong. Next question, guys, is Taylor series. Okay, so you learned, let's just say, we learned, when we go to school, we learn basic operations, addition and multiplication. And then we begin to learn more and more operations, square root, integration, derivative, and who knows what not, right? So the simplest operations are operations that can be described only in terms of multiplication and addition. Good. And then more complex operations, they use n fruits or integrals or anything else like that. Okay. So the simplest function you can come up with, it's a polynomial. Okay. And what is a polynomial truly? Why anybody is interested in polynomials? That's because they only involve addition and multiplication. Okay. So if you create any function that takes an input and all it does in its process is adds and multiplies numbers, you can group, like what we learned to do, you can group by the number of times we multiplied by x. So here, no multiplication by x. Here is multiplication by x once, twice, all the way to the nth power. You understand? So pick, we can, if you don't understand my point, we can stay after class, I'll show. I showed it to my calculus students, okay? Pick any operation involving addition and multiplication. You can rearrange it in terms of how many multiplications by x happened, okay? No multiplication by x, one multiplication by x, 2, 3, 4, all the way to n, okay? And that gives you the polynomial form. But why is this form interesting? It's because that form is unique to operations involving only multiplication and addition, nothing more. Clear? Any such operation involves only addition and multiplication, and conversely, any operation where you only use addition and multiplication can be rearranged to be looking in that polynomial form. Clear? Now, let me ask you this weird question. Is the root of x a polynomial? So Andres says no, Aaron says no. Now, guys, clearly root does not look like a polynomial, but let me actually tell you more. When you say, let's say, root of 25, you don't have an operation in your mind. Do you agree? when you say root of 25, you think, well, let me find a number that when multiplied by itself gives me 25. And you guess it's equal to 5. Based on previous experience, just search, okay, 1 times 1 is 1, 2 times 2 is 4, right? And then you go to 5 times 5 and it's 25, and you guessed. Now, if I ask you to calculate root of 5, you're stuck, right? Because you don't know what's root of 5. I mean, you never saw a number squared that's equal to 5, but you type it in your calculator and it spits digits, okay? Now, what does a calculator do, right? The calculator, I mean, maybe it has, it's a complicated machine, but most machines, it boils down to addition and multiplication, you understand? So when I ask, is root of x a polynomial, I am asking, is it possible to come up with a procedure that only involves addition and multiplication that will represent root of x as a polynomial? Would tell you, if I take 5, what do I do to 5? Do I multiply 5 by something? Do I add something? Do I subtract something, right? Can I carry out a polynomial procedure to obtain root of 5? So if you say no, can you give me a justification why you are claiming it's impossible to carry such procedure? Any ideas? So you understand my question is reasonable, correct, guys? When I ask, is it a polynomial, I'm asking, can you simulate the operation of taking roots by just using addition and multiplication? And if the answer is yes, then root of x is a polynomial. I can create a formula for it. And if the answer is no, that means no formula involving only addition and multiplication can be possible. Very good, Jack. Okay, so if x is, we can reason like maybe Jack suggested. Okay, so we know that addition and multiplication is capable of processing any number, right? You can process positive numbers and negative numbers if you create such an operation, but root of x, well, root of x can only process positive numbers, or so it appears. All right, so on the surface of things, root of x cannot be a polynomial because it fails to digest negative numbers, whereas any polynomial operation will be able to digest every single number. Do you understand? So it seems that root of x is not a polynomial. Of course, here is something that we can tell, guys. I can actually show you how to think about it, if you would like. At least what we see is that if we use finitely many additions and multiplications, finitely many, we will not be successful based on that observation, possibly, okay? You can think about it a bit deeper, but you see, we find something that all polynomials have, and that's the ability to digest every real number. And roots do not have that ability necessarily. But of course, I can take root of maybe cube root. Cube root can digest any number, Jack, right? Is cube root a polynomial or not, right? Cube root can digest any number. Is there anything else that happens that's not gonna work well? Good. So you can think of such arguments, and then once you come up with one, you can understand that it is impossible to use a finite polynomial and calculate root of any type, okay? A finite polynomial will not successfully compute root of any type. However, if I use infinitely many operations of addition and multiplication, I can nonetheless carry out such calculations. You understand? So many more things, at least locally, are infinite polynomials. Okay? And those infinite polynomials are known as power series. So the difference is just instead of stopping somewhere, you continue going on. Okay? And let me show you how you can construct it. So this infinite polynomial, it's just you don't stop with the highest power, you just keep multiplying by x to higher powers. That's called infinite polynomial in my language. In a power series, that's how it's known in calculus. Okay, so let me show you how that works. Suppose we want to represent e to the x as a power series. Can we do that? Is e to the x a polynomial? Well, it's clearly not a finite polynomial. Do you agree? Because any finite polynomial, let's say if the polynomial is of degree 5, take 6 derivatives and it's 0. And e to the x, no matter how many derivatives you take, it's not 0. Right? So that means that e to the x cannot be a finite polynomial. But if you have an infinite polynomial, it doesn't disappear after many, many derivatives. Good? And that's what we're going to try to do. So we'll do it abstractly. Okay, guys, so suppose that I am successful in finding an infinite polynomial to represent e to the x. So it's something like this. All I have to figure out are what my coefficients a0, a1, a2, and onwards. How do you figure out, let's say if you remember or can guess, how do I know what is a0? So I have e to the x, that's e to the x, okay? Equal to a0 plus a1x, blah, blah, blah. How do I figure a0? What's the simplest way to figure out a0? Well, eventually, but just a0, Andre. A0, it's not so hard, right? Look at it, because it begins with what is the easiest way we do? Yes, f of 0, exactly, right? Why you plug f of 0? Because look at it, e to the 0, we know it's equal to 1, yes? E to the 0 is the only easy value for exponential. E to the 0 is 1. Plug in 0 in this polynomial, it annihilates all instances except for a0. You understand? We develop a nice strategy. So a0 is very easy. Here it is, guys. F of 0 is equal to a0. So if I plug in 0, I get this situation. That's basically, I'm here deriving, in fact, for any function. You can think of e to the x, but any function that I can easily evaluate at 0. Okay? So f of 0 is a0. Now, why do I take derivative for the next term? Because look at it, if I take derivative, if derivatives work like they did before for finite polynomials, you know, you have this power rule. The power drops and you have this expression, right? So the a0 disappears because it's constant, and then you have a1 plus whatever else remains. You see what I did? I was able to make a1 a lonely guy, not attached to any x. Put 0 instead of x now, and you get a1. You follow why I take derivatives? Yes, guys, because derivatives give me a very easy tool to isolate the next term, right? If I plug other values, or if I do something else, I have all the infinitely many terms to contend with. But here, plug in 0, I got a0. Take the derivative, a0 is eliminated, and a1 takes its place. Good? So we have f prime of x is equal to this expression, and so f prime of 0 is a1. And so what is the general situation, guys? In general, if I want to calculate a sub k, I will have to take k derivatives, right? K derivatives. So x to the k drops, then it's k to the minus 1, it drops, then k to the minus 2, it drops. It will drop until I get k factorial times ak. Here it is, guys, right? It's k factorial, ak plus k plus 1, blah, 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 right? And so when I plug in 0, I get k factorial times ak. Are you with me? And so I see that ak is the k derivative divided by k factorial. And I have this is called Taylor series form. You see here, I presume it's easy for me to calculate the value of the function at 0 and at all values. And in fact, the function has to be infinitely differentiable to be so representable, right? Because the process will, you can prove, I mean, you have all sorts of technical things to eliminate, guys, right? You see, Jack, what I'm doing is not fully rigorous because I have to explain there are many questions that can arise. Can I take derivatives of infinite polynomials? What does it mean to take derivatives of infinite polynomials? Will they produce the same result? Right? There is issues of convergence. There are all sorts of many issues to be verified, but they distract from the idea. The idea is very simple, is that I really like everything to be simple. And the simplest operation is multiplication and addition. And so if I fail to make it work for finitely many additions and multiplications, I hope to be successful if I allow infinitely many operations of addition and multiplication, which I represent as a power series. You understand? I extend the idea of polynomial to allow the process to go forever, potentially. And I have this formula. Okay? And here is what happens with e to the x. Since any derivative of e to the x is e to the x, when you plug in 0, all the derivatives at 0 are equal 1. So that means that 1 divided by k factorial x to the k, the summation. This summation is e to the x. You understand? That's going to be very important, guys. E to the x, and it's in all its forms will be appearing again and again in this class. So it's important to understand all those limits. You understand the limit that I began with and the e to the x that we have here. So here you can see that the summation from 0 to infinity of 1 over k factorial is e. The summation where you have 5 to the power of k over k factorial is e to the power of 5. Minus 3 to the k over k factorial is e to the minus 3. You see? So just any number to the power of k divided by k factorial, if you add it up from 0 to infinity, will be equal to e to that number. Good? Wonderful. Do you have any questions about this review, guys? Do you want me to go over any of those ideas again? All right. Since we have, so no questions? Okay. Give me a second. Then I will stop this recording and I will show you something that you might enjoy because you have a chance to be correct this time, okay?